Multi-tenant HDFS usage patterns, architecture, management, and best practices, a comprehensive technical overview based on industry research and implementation best practices. This presentation will guide you through the core concepts, architectural components, and operational strategies for effectively implementing a multi-tenant Hadoop Distributed File System. We will explore the economic drivers, the detailed architecture, and the best practices for managing a shared HDFS cluster that serves multiple users and groups securely and efficiently. Let's begin by defining multi-tenancy in the context of Hadoop. At its core, multi-tenancy refers to the practice of having a single, shared Hadoop cluster so multiple independent users or groups, known as tenants. This model is built upon several key aspects. First, resource guarantees and quotas, which ensure that each tenant receives their fair share of cluster resources like storage and compute, preventing any one tenant from monopolizing the system. Second, security isolation and data protection. This is paramount. It involves ensuring that tenants cannot access each other's data without explicit permission, safeguarding sensitive information through mechanisms like authentication and encryption. Third, quality of service, or QoS. This involves managing and prioritizing cluster performance to meet the specific performance and latency requirements of different workloads and tenants. And finally, administrative autonomy. This allows tenants to have a degree of self-service and control over their own allocated resources without needing constant intervention from the central cluster administrators. Now, let's discuss why organizations are increasingly adopting a multi-tenant model. The drivers are primarily economic and operational. The first driver is cost optimization. Maintaining a single, large shared cluster is significantly more cost-effective than managing numerous smaller, private clusters. It allows for the consolidation of infrastructure and reduces overall hardware and maintenance costs. The second driver is operational efficiency. A multi-tenant setup enables centralized administration. This means patches, updates, and security policies can be applied once across the entire cluster, drastically simplifying management and reducing overhead. The third driver is scalability. A shared cluster allows for elastic resource allocation. Resources can be dynamically reallocated between tenants based on their current needs, leading to much higher overall utilization. To put this in perspective, consider an economic comparison. A single-tenant cluster model often has a low initial cost but high ongoing costs due to duplication of effort and infrastructure. Its utilization rate is typically low, around 30 to 40%. In contrast, a multi-tenant cluster has a moderate initial cost but low ongoing costs due to consolidation. Most importantly, it achieves a much higher utilization rate, typically between 70 and 85%, maximizing the return on infrastructure investment. Let's delve into the architecture of a multi-tenant HDFS cluster, starting with node allocation strategies. First, master nodes. These critical nodes, which include the name node and resource manager, are configured in a high availability, or HA, setup with automatic failover. This ensures the cluster remains available for all tenants even in the event of a hardware failure. Second, worker nodes. These are the data nodes that store and process data. They are shared across all tenants, but their resources are partitioned logically. This means CPU, memory, and disk space on these nodes are allocated and guaranteed to specific tenants using resource managers like Yarn. Third, edge nodes. These are tenant-specific gateway nodes used for data ingress and egress, that is, for moving data into and out of the cluster. Each tenant may have dedicated edge nodes to provide isolation and security for their data pipelines. And finally, management nodes. These are dedicated nodes for cluster monitoring, management, and orchestration tools like Ambari or Cloudera Manager. They ensure the smooth operation of the entire shared environment. Now, let's examine the storage architecture for a multi-tenant HDFS. To ensure scalability, especially for metadata operations, we often use a federated HDFS. Federation employs multiple independent name nodes, each managing a portion of the file system namespace. This prevents the metadata of one tenant from impacting the performance of another. The standard replication factor for data blocks is 3. This replication is configured with rack awareness. This means copies of a data block are strategically placed across different physical racks within the data center. This protects data against the failure of an entire rack, enhancing availability. This leads to multi-rack distribution, a best practice for high availability. It ensures that the cluster remains operational even if a network switch or power unit for an entire rack fails. Finally, meticulous capacity planning is essential. We must allocate not just space for tenant data, but also reserve capacity for the operating system, application logs, and potential data dumps. This prevents the cluster from running out of space for critical system functions. Our final architectural focus is on namespace partitioning, how we logically separate tenant data within the shared physical storage. HDFS federation, which we mentioned earlier, provides isolated namespaces. Each tenant can be assigned to a specific name node and namespace, creating a strong logical boundary. A more common method is directory segmentation. This involves using a structured directory hierarchy within a single namespace. For example, each tenant has a dedicated root directory, such as /user/tenant1, /user/tenant2, and so on. Access controls are then applied at these directory levels. This isolation extends to higher level services. In Apache Hive, we create separate databases for each tenant, so tenant 1 would have its own Hive database, completely separate from tenant 2's database. Similarly, in Apache HBase, namespace-based isolation is used. Each tenant is assigned their own HBase namespace, which contains their tables and data, providing a clean and manageable separation layer within the NoSQL store.